Shiven, wait.
otherwise I stop streaming because
Hello students. So today we are back with another conceptual topic on capacitors, and in this topic we will be generally focusing on the circuit part of capacitors, which is considered as somewhat difficult topic by the students. And in this circuit analysis we will try to cover some basic circuits involving capacitors, how to do the reduction of circuits, so some basic circuits, then how to do reduction of circuits, and then also we will see some complex cases involving capacitors, right? So in our today's lecture we will focus only on the circuit theory of capacitors and understand how these circuits can be solved. And before we jump in, we know there is a very important basic that we need to understand, which is called as what, beta? Series and parallel combination. Correct? Series and parallel combination of kya beta? Capacitors. So in a series and parallel combination of capacitors, what we need to understand, there are two things which we need to keep in mind before starting solving the circuit. So this is, say, one capacitor, and in series it is connected to another capacitor. I call this capacitor beta C1 and this is called as what? C2. Fine. So if this entire system is having terminals A and B, so this is terminal A and this is terminal B, and this entire system is connected to some kind of a power source, say battery of some V volts. Now what happens when the moment you connect the battery to this circuit, then the charge starts flowing, correct? The rate of flow of charge is called as what, beta? dq by dt, which we also call as the instantaneous current. So the charge starts flowing from battery to the initially uncharged capacitors, and then what happens, this potential V gets distributed or gets divided among the two capacitors. So some potential goes to capacitor C1 and some potential is developed across capacitor C2. But if you look at these two capacitors, these two are connected in what, beta? Series. So whatever rate of flow of charge is in this line of the circuit, same will remain in this line of the circuit, same will remain in this line of the circuit, and so on. So what we need to understand is the charge which flows through C1 as well as C2 in a series combination. This is which combination that we are talking about? Series combination. In this series combination, the charge flowing in C1 will remain same as the charge flowing in what, beta? C2. So potential gets divided. So there is a rule for series capacitors, and the rule is called as what? Potential divider rule. The potential gets divided, but the charge remains same for C1 and C2. There are many other reasons which support this explanation, which we'll see in our circuits that we are going to do today or solve today. And before we jump onto the parallel combination, we need to understand what series means. You can consider two vectors, say vector A, and you can consider another vector B. And if these two vectors are connected such that head of one vector is connected to the tail of another vector, head of one vector is connected to the tail of another vector, and there is nothing else in this junction, or there is nothing else that is connected in this junction. That means I can consider this capacitor as one vector, this capacitor as another vector, and the head of this vector is connected to the tail of this vector, and there is nothing else at this junction. So then these two capacitors are called as what combination, beta? Series combination. Understood? Now let us go to which combination? The parallel combination. So in parallel combination, what we need to understand is we have two capacitors. One is C1, same two capacitors I am taking, and it is connected in parallel to another capacitor which I call as what, beta? C2. So this is C1 and this is what, C2, and say these are terminals. This is terminal A and this is terminal B. So what I am doing is I'm connecting these two terminals across a battery, and this battery has a potential of what, beta V. Again, charge will start flowing dq by dt, rate of flow of charge, correct, which is the instantaneous current at any instant. When this current flows in this part of the circuit and then reaches junction A, it gets divided into two parts. It gets divided into two parts, and we can see that some charge, say Q1, goes to C1 and some charge flows toward beta Q2. So the total charge which was given by battery, total charge which was given by what, beta, battery, gets divided into the charge with C1 plus the charge in what, C2. Unlike the case of series where potential divided, here what divides charge. So this parallel combination is also called as what, charge divider, is also called as what, charge divider. And what remains constant? You can see this battery terminal, this capacitor terminal, and this capacitor terminal, they all are in parallel to each other. They all combine at junction A and junction B on one side and on the other side. So the potential of the battery is same as the potential of capacitor C1 and is same as the potential of what, beta, capacitor C2. So in parallel, the potential across the capacitors remains constant, and in series, the charge across the capacitors remains what, beta, constant. And how to understand this as far as, say, vector notation is concerned? So if you have two vectors which are lined at 0 degrees with each other, parallel vectors, right? And then if you connect, it's a very simple example. And then if you connect, in this manner, say the tail of one vector is connected to the tail of another, and the head of one vector is connected to the head of another, right? And there is nothing in this region. There is nothing in the connections. This connection should not have another vector on it. This connection should not have another vector on it. Then these two are considered as what, parallel. For example, in this case, this capacitor is one vector, this C2 is another vector, this tail of C1 is connected to tail of C2, and head of C1 is connected to head of C2. So we call that these two vectors are in which combination, beta, parallel combination. So these are few important points which we need to understand before we start circuit analysis. So going next, for example, if I take this question, if charge on left plane of 5 microfarad capacitor in the circuit segment shown in the figure is 20 microcoulomb, so 5 microfarad, so I have this capacitor which has a charge of 20 microcoulomb on it, right? The charge on the right plate of 3 microfarad capacitor is, so we have to find basically the charge on the right plate of 3 microfarad capacitor. Is it clear? So this has beta 20 microcoulomb charge. Now you can redraw this circuit, which we also call as reduction or vector diagram. What is the vector diagram? This is one vector here, then we have another vector here, then we have another vector here, then these two vectors are again joining here, and then we have another vector here. So what has happened is there is a charge of 20 flowing in this part of the circuit, which will get divided among these two portions, right? And if you call this capacitor as C1 and beta this capacitor as C2, I can see that 3 microfarad and 4 microfarad are in parallel to each other. If they are in parallel to each other, the charge will get divided between 3 microfarad and 4 microfarad. So if this happens, this 20 microcoulomb, when it reaches this junction, say I call this junction as A, it will get divided among these two capacitors. Because this capacitor C1 and this capacitor C2 are in parallel, so potential difference across the capacitors, I will first take an elaborate method and then tell you the shorter one. Now in capacitor, what is the definition of capacitor? Capacitance, any body capacitance, if I have to calculate, what is the definition of capacitance? Capacitance ka definition, Q, you know from mathematics we write Q is equal to what, beta? Cv. This is a mathematics, but what is the definition of capacitance? It is the charge on either plate, any one of the plate of the capacitor, charge on either plate divided by the potential difference between the plates. Samjha? It is a charge on either plate, any one of the plates, one will have positive, another will have equal amount of negative charge divided by potential difference between the plates. Now in parallel for C1 and C2, the potential difference is constant. So that means the capacitance is proportional to the charge on either plates of this capacitors. For only which combination beta? For only parallel combination. So in parallel combination, capacitance ratio will decide the charge ratio, or I will say C1 by C2 will be equal to the charge on 1 divided by the ratio of. Clear? So how much is C1 and C2? Now if we solve this question, if we have understood what parallel combination means, so how much is C1 and C2? C1 is beta 3 and C2 is 4, so 3 by 4 must be equal to Q1 by Q2, which gives us a relation that 3 times Q2 is equal to 4 times Q1. This is our one equation. Another equation from the junction itself, total charge is 20. This 20 gets splitted in C1 and C2, so sum goes, Q1 goes here and Q2 goes here. So simply my second equation is 20 is equal to Q1 plus Q2. And if we solve those two equations, which is basically the parallel combination of two capacitors, we can get our result, and our result will be 20 will be equal to Q1 plus, instead of Q2 I will write 4 by 3 Q1. I hope you have understood. It is a simple substitution, and when I do this substitution, it is 7 by 3 Q1. It is 7 by 3 Q1, so this is 60 by 7 microcoulomb is the value of Q1. So our answer is either plus 8.57 or it is minus 8.57. So now charge is flowing in this direction, and charge flows from higher potential to lower potential. Charge is flowing in this direction, charge flows from higher potential to lower potential. It means this plate of the capacitor is positive and beta this plate of the capacitor is what? Negative. They are asking about the right plate of 3 microfarad capacitor. So the right plate of 3 microfarad capacitor is this plate. So this is a negatively charged plate. So my answer would be minus 8.57 microcoulomb. Clear? So this is one question which we have done in a very elaborate manner to understand what parallel combination actually means. Let's go next and understand few more concepts. I am taking some questions today with which I will cover some theory also to understand the things better, because this is the best thing to learn circuits. You cannot learn circuits by directly going to the problems or directly solving the problems. You have to understand what are the methods to solve the problems, and those methods I can tell you while solving the problem itself. Say I have one more problem here. In the circuit shown, the energy stored in 1 microfarad capacitor is. So we have different capacitors here. This is a 3 microfarad capacitor. Then this is a 24 volt battery, right? And then beta we have this 4 microfarad capacitor. This is 1 microfarad capacitor and this is 5 microfarad capacitor. Correct? Before jumping on to the energy, my first question to you will be, I will rephrase this entire question. My first question to you is, how much is C equivalent across the battery? How much is C equivalent across the battery? So across the battery, what is C equivalent? I can see this capacitor, this is one junction, this is beta another junction, this is beta another junction, and this is another junction, right? I can see this 5 and this 1. These two capacitors are in series or parallel? They are in parallel, right? They are in parallel, and I will write here what are the rules for parallel and series. For parallel, the rule is you simply sum the capacitors, and for series, the rule is product divided by sum, right? So now if I look at 5 and 1, I will name these junctions. This is junction A. I will do this question in as much detail as possible, and let's see where we land. So I have 4 junctions in this. One is A, one is B, one is C, one is D. Now if I see between junction B and C, 5 and 1 are in parallel, correct? So 5 and 1 are in parallel, so the combination will give us the sum of these two as mentioned here. So my answer for capacitance between B and C will be how much beta? 6 microfarad, right? Similarly, between what is the capacitance between A and C? A and C, one is 3 microfarad between A and B, so I will write it as CAB, and CAB is in series with what beta? CBC. So this capacitor 3 microfarad is in series with this entire combination. I hope you all agree with that, right? And when this is the case, when it is series combination, the rule is product by sum. CAB is beta 3 and 3 is in series with CBC is 6. So your answer will be 3 into 6, 18 by 9, which is 2 microfarad, right? And now we know this fact that this entire portion has a total capacitance of how much beta? 2 microfarad. And if you look at these junctions, junction D and junction A, I can see that this green surface, this entire green surface is in parallel with this capacitor 4 microfarad. Do you agree or not? This is one vector, correct? And then this is the other vector which is coming here, right? And A and D are the terminals between these two capacitors. So this green portion has a capacitance of 2 microfarad. This has a capacitance of 4 microfarad. I can also reduce this circuit and redraw this circuit in this form. I will say this is now left or reduced to one capacitor 2 microfarad. This point is A and this point is D, and then I have one more capacitor which is beta how much? 4 microfarad, right? And then there is this battery which is how much beta? 24 volt. So now you can see that these two capacitors are now in what? They are simply in parallel combination, and if this is a simple parallel combination of 2 and 4, my C equivalent across the battery, that is this result would be 2 plus 4, and my answer is how much beta? 6 microfarad. So I have completed first part of the question where I have tried to calculate what? I have tried to calculate the total capacitance of this circuit. Is it clear? I'll take each capacitor in this and see what our results are going to be. So this is my first question to you. My second question to you from this entire problem is how much charge is given by the battery. See, very basic questions, but we need to understand them. How much charge is given by this battery? So battery gives how much charge here? Say call that charge as Q. Potential of the battery is how much beta? 24 volts. What is the C equivalent as seen across the battery? It is 6 microfarad. So this entire circuit has a 6 microfarad ka capacitance which is being supplied by a power source of 24 volts. So how much charge this power source will supply to this 6 microfarad? So Q equal to CV, and C equivalent into potential of the battery. This is the charge given by the battery. This is the equation that you will always use, and my answer will be 6 into 24, which will be 144 microcoulomb. 144 microcoulomb is the amount of charge that this battery is given. So I have done two parts of this question. One, what is the C equivalent across the battery? Second is what beta, how much charge is given by the battery. Is it clear? Is it clear? So now let us, can we also find, this is the charge given by the battery, can we find how much charge is present on each capacitor? Can we find how much charge is present on each capacitor? So for that, if I redraw this circuit, this is beta your 3 microfarad, then we have this 5, then we have beta this 1, this closes here, then we have this 4, correct, and then we have our battery of how much? 24 volts. This is 3, this is 5, this is 1, this is 4. All units are microfarad. I know total charge coming from here we have just calculated is how much? 144 microcoulomb. I'm not mentioning the units here. So this 144 reaches here, correct, and it gets divided. It gets divided in such a way because I know the capacitance of this portion. The capacitance of this portion was how much beta? 2, and this is how much? 4. So this 2 and this 4 are in parallel. So if they are in parallel, C1 by C2 must be equal to what beta? Q1 by Q2. C1 by C2 is 2 by 4, must be equal to whatever is Q1 by Q2, or I can say Q1 is equal to Q2 ka half, correct? And second is, I know Q1 plus Q2 is how much? What is the total charge that is entering this junction, and then some Q1 is going here and some Q2 is going here. The total charge that is entering this junction is how much beta? 144. So this is how much? 144. Or instead of anything, say instead of Q1 if I write Q2 by 2, so this becomes 3 by 2 Q2 is 144, or Q2 will be how much beta? 288 by 3 microcoulomb, which is nothing but charge on this 4 microfarad capacitor. Is it clear? Charge on this 4 microfarad capacitor. Now if I also have to find how much is Q1, how much is Q1? Q1 is Q2 ka half, so it is 288 by 6 microcoulomb, and Q1 is the charge that goes here. So Q1 is the charge which is there with this 3 microfarad capacitor, and this is 288 by 6, correct? This is 288 by 6, and if you do this division you will get 48 microcoulomb. So this is beta 48 microcoulomb which reaches this junction, and then 48 microcoulomb gets divided into the ratio of 1:5. So for this region 1:5, what will I write? 5 by 1 should be equal to, correct, Q1 by Q2. That means Q1 is beta 5 times Q2, correct? And we know Q1 plus Q2 for this part of the circuit is how much? 48. Or I will write Q2 is equal to 8 microcoulomb, and beta Q1 is equal to how much? 40 microcoulomb. So now let us summarize. What are the charges on which capacitor? 3 microfarad capacitor has a charge of how much beta? 48 microcoulomb. 5 microcoulomb farad, sorry, farad. 5 microfarad capacitor, bigger capacitor, correct? Bigger capacitor, bigger charge, 40 microcoulomb. This is the calculation that we did. Then 1 microfarad capacitor, how much charge? It has 8 microcoulomb charge. Then we have this 4 microfarad capacitor which had a charge of Q2 which was equal to 288 by 3 microcoulomb. So till now what we have done is we have calculated charge on each and every capacitor, we have calculated C equivalent of this circuit, and we have also calculated what beta total charge given out by this battery. So almost entire operation of this circuit we have done today, or the surgery of this circuit we have done today. And now let us move one step further and try to find energy stored in these capacitors. So if we try to go a little further, I will write here, this is your 3 microfarad capacitor, this is your 5 microfarad capacitor, this is 1 microfarad capacitor, this is 4 microfarad capacitor. How much is the charge on each of these capacitors? This is 3 microfarad capacitor. If you remember, it was 48 microcoulomb. This is 5, it had 40 microcoulomb. This is 1, it had 8 microcoulomb. This is 4, this had 288 by 3 microcoulomb. Now what is the energy stored in these capacitors? Energy stored is given by what beta? Q square by 2C. So 48 ka square upon 2 into 3. Similarly, this will be 40 ka square upon 2 into 5. This will be 8 ka square upon 2 into 1, this will be 288 by 3 ka square upon 2 into 4. So not only the energy stored in one particular capacitor, but we have calculated, by these calculations you can find energy stored in each and every capacitor, of this particular circuit. There are other formulae to find the energy of any capacitor. Other formulae include in terms of capacitance and potential. Correct? For this, to apply this formula, I should know the potential across any particular capacitor, which I can easily calculate because I know V is equal to Q by C for any given capacitor. So say I take this capacitor, I know the value of C, I know the value of Q, so I can find what is the potential across 1 microfarad capacitor. So this value will be Q by C and it will be 8 by 1, which is beta 8 volts. Similarly, you can find potential across any of these capacitors: 3 microfarad, 5 microfarad, 4 microfarad, 1 microfarad. Things are very simple. When we look at circuits, it looks like a very complex thing, but if we go step by step and follow proper definition of series and parallel, the things become very easy for us. I hope this statement, this problem is clearly understood. Fine, let us proceed further and see some more cases where only something is asked about the capacitance of the circuit and nothing is asked about the charge or potential or energy possessed by that particular circuit. So it is a simple question. If you see what is the equivalent capacitance of a system of capacitors between A and B, it is a simple question of reduction. The terminals are given as A and B. So first I need to understand or visualize, or I need to imagine which capacitors are connected in series and which capacitors are connected in what beta? Parallel. So first, when I looked at this circuit, this was the first eye-catching point, that these two capacitors are connected purely in series and there is nothing present at this junction. So these two capacitors are in series. So your answer would be how much beta? Product by sum. C into C, C square divided by C plus C, 2C. So this is simply what? C by 2. I cannot see anything else in direct series or parallel. So I will stop here and I will now go to the reduction of this circuit and see how this circuit behaves next. But before that, I want to draw your attention towards this capacitor. This capacitor, if you look, these are the junctions of this capacitor, right? And if you look at this branch of the circuit, this branch of the circuit is in parallel with this branch of the circuit. Why? Because they have common junctions. If you consider this as one vector and beta this as another vector, what I told you, the tail of one vector must be connected to the tail of another vector and the head of one vector must be connected to the head of another vector, and there must be no other capacitor on these connections. Same as what we are seeing. So what we can conclude is that these two surfaces are in parallel with each other. So this surface has a capacitance of C by 2, this has a capacitance of C. So the parallel combination of these two, I will call this as junction A and junction B. So the net capacitance between A and B will be C parallel with C by 2, and your answer is simply sum of these two, which is 3C by 2. Beta clear? Now I will reduce this circuit and I will make it of this form. This was your junction capital A, this is beta C, correct? This is another capacitor C, this is small a, this is small b. Now what has happened between this small a and small b? And then this small b is same as capital B. Why? Because there is no capacitor present between small b and capital B. So these 2 points are same points. They are same points. So you can coincide capital B and small b and show them as same points. Now what has happened between the capacitance between A and B? These two have come in parallel with each other, and my total capacitance between A and B has become how much beta? 3. Oh, okay. So I had drawn a resistor, capacitor, and its capacitance is how much? 3C by 2. This is beta C, this is C, this is 3C by 2. I hope you understand what to do next. A very easy step. I feel these two are in series again. Correct? There is nothing at junction A. So C and 3C by 2 in series means the equivalent will be product C into 3C by 2 divided by C plus 3C by 2. So which will give us an answer of 3C square by 2 upon beta. This is 5C by 2 and my answer will be 3C by 5. So this is the answer to this surface ka capacitor. And then if you look at points A and B, so these two surfaces, blue surfaces, are in parallel again because this branch and this branch come in parallel to each other. So this is C, this is 3C by 5. So my C equivalent between A and B is the parallel combination of C parallel to what beta? 3C by 5, and my answer would be sum 8C by 5. 8C by 5. And if you do calculations, then your answer would be 1.6 because 16 into 5 is 80. So that's how we solve circuit questions. This question only, no battery is given, no charge flow is given. It is just an untouched capacitive circuit which has never been charged, and just capacitors have been connected with each other, and they are just asking you the equivalent capacitance of the circuit. Moving further, in the circuit shown, what is the ratio of the charges on 5 microfarad and 4 microfarad capacitor? 5 microfarad. Now beta, we have learnt everything. I will not do elaborate things. Let us finish this question without even using the pen. Let us start. These two and 5 are in parallel, so their equivalent will be 7. This 7 is in series with 3, so equivalent of 7 and 3 will be product by sum. So this is 2.1, and then this entire is 2.1, and 2.1 comes in parallel with 4, so again sum. So your total is 4 plus 2.1, which is 6.1. So your C equivalent for this circuit is how much beta? 6.1 microfarad. And now you have to find ratio of charges on 5 and 4. So total battery is how much beta? 6. So what is the charge given by this battery? The charge given by this battery, which I have told you, Q is equal to CV, equivalent capacitance into potential of battery. Equivalent capacitance is 6.1, potential of battery is 6. So this gives you 36.6 microcoulomb charge comes out from this battery. And this 36.6 microcoulomb charge gets divided at this junction. Some goes up, some goes here on the sideways, and we can see how much charge goes up, how much charge goes sideways. I can call this as Q1, I can call this as Q2, and we can use the same rules of division of charge in parallel circuits. So I can simply say the upper part has a capacitance of how much beta? 2.1. The lower part has a capacitance of how much beta? It has a capacitance of 4. So 2.1 and 4. So the circuit is something like this. This is 2.1, and below it we have 4, and then we have a battery which is 6 volts. We have a 6 volt battery. This is giving out 36.6 microcoulomb. This charge is getting divided into these 3 capacitors. So I will simply write 2.1 by 4 will be equal to Q1 by Q2, and also I know Q1 plus Q2 is equal to the total charge. We have been doing questions. This is our almost third question on the same concept, correct? And we have 2 equations, we have 2 unknowns, and we can directly calculate the values of Q1 and Q2. This is your homework to find the value of Q1 and Q2 and mark the correct option in this, whether it is 4 by 5, 3 by 5, 3 by 8, or it is what beta 1 by 2. Clear? This is one way of doing this question, right? The way that we have been learning, we have been understanding. There is another way of doing this question, which we call as potential divider, which we call as what? Potential divider. How we can solve this question using potential divider method also. So that also I will tell you. So for potential divider method, I'll erase this, all these surfaces, right? For potential divider method, I know this is 6 volt, right beta? So potential across this capacitor is also how much? 6 volt. Now this is beta 7 and this is 3. So I know potential will get divided among 3 and 7. I know potential will get divided among 3 and 7, and I know whatever charge flows here, say Q1, same charge will enter this junction also, this will also this junction. So this will also be how much beta? Q1. Clear? So if I find potential across this junction, this part of the circuit, I know this is 6. If I find potential across this part of the circuit, my question is done, because Q is equal to CV and I can find how much charge is on 5 or how much charge is on 4 and so on. Is it clear what I'm going to do next? So what I'm going to do next is solve this question using another method, which is called as the potential divider method. And what I will do in that method is very simple. See. So potential across 4 microfarad I know is 6 volt. So charge across 4 microfarad, very easy, Q is equal to CV. So C is 4 microfarad and potential across this is 6. So this is beta 24 microcoulomb. So my first or my one thing about the question is solved. What is the charge on 4 microfarad? That I have done. Now I am left with 5 microfarad. For 5 microfarad, what I do is this 6 volt gets divided into 3 as well as this combination. So potential which goes to 3, I will call it as V1, and potential that goes to this combination, I will call it as V2. And I know V1 plus V2 must be again equal to 6, as I have dealt earlier today. This is called as potential divider method. So V1 plus V2 is equal to 6. If V1 plus V2 is equal to 6, we know that, V1 and V2 are in series with each other. Do you agree? V1, this 3 microfarad capacitor, and this combination 7 microfarad capacitor, they are in series with each other. When they are in series, the charges remain same. Q is equal to CV. That means C1 by C2 will be same as what beta? V2 by V1. Will be same as what? V2 by V1. So I know one is 3, another is 7. One is 3, another is 7, and so I will write this as V2 and this I will write as V1, and I will get V2 is equal to 3 times V1 by 7, and if I substitute it here, I get V1 plus, instead of V2, 3V1 by 7, and this is beta 6, and this is 10V1 by 7 equal to 6, and what we get is V1 ka value will be 24 by 5 volt. You can check 7 plus 3, 10, correct? And 10 by 7, 42. I'm sorry, I think it will be 21 by 5. 42 by 10, so 21 by 5. So what is V2? So V2 will be 3 by 7 into 21 by 5, which is beta 9 by 5, which is how much? 9 by 5. So potential across this is how much? 9 by 5 volts. What is potential across 4 microfarad? It is 6 volts. Clear? What is charge on this 4 microfarad? It is 24 microcoulomb. So we can find what is the charge on 5 microfarad farad. Q is equal to CV. So C is 5 and V is 9 by 5. So this is beta 9. This is how much? 9 microcoulomb is the charge on 5 microfarad capacitor. So what is the ratio? So on this it is 9 and on this it is 24. So our ratio is 9 by 24 and that is 3 by 8. That is how much beta? 3 by 8. So my answer is this one. There are two ways to do such questions. One is you use the charge divider method throughout your problem and find the solution, which we have already done in previous questions. So I did not take that method in this question. Another method is to find the same solution using the potential divider method. Potential divider method can be used when you have things in series. For example, here if I see this part of the circuit is in series with this part of the circuit, so I can use potential divider and I can say total potential is 6 volts and this 6 volt is getting divided into V1 and into V2 and V1 plus V2 is also how much beta? 6. So then you get this ratio. And to summarize this all, so if what I have told you earlier today, if it is parallel, then the ratio of capacitance is same as the ratio of the charges. Very important. And if it is series, then the ratio of the capacitances is inverse ratio of the potentials. Correct? And all your questions can be solved by this trick. And it becomes a question of more of a question of a ratio proportion than question of a capacitors when we see things in such manner. Right? So we have done few problems today on charge and potential, and also we have tried to calculate the equivalent capacitance of certain systems. So before I finish, I would also like to draw your attention towards one more important type of circuit, or one more important type of circuit analysis which is asked in capacitors, and this analysis is regarding a concept which is called as time constant. Which is called as what beta? Time constant. So the questions that you will find is, to find the time constant you have to what? Find this constant for a given circuit. So a given circuit will be there and you will be asked to find time constant for that given circuit. Fine. So what we have to do is, I'll just take an example here. Say this is some R, this is beta some C, and this is a battery, and this is beta another R, and then say this is another R. Clear? So you have to, this is say R, this is R, this is beta V, this is R, and this is what? C. Very important concept, and there is a trick in this question. So please listen carefully. So there are certain steps to find time constant. First thing is, what is the formula of time constant? Formula of time constant is R equivalent as seen from the capacitor. R equivalent as seen from the capacitor terminals. If I look from this, if I sit on this capacitor and I look from its terminals, what is the R equivalent of this circuit? That is what you have to write here, multiplied by the value of this C. Fine. How to find this R equivalent? Step number 2. Short circuit all batteries. Short circuit what beta? All batteries. Number 3. Find R equivalent by open circuiting the capacitor. So this 3-step process is what we have to follow. Let us follow this process step by step. So what this process says? So the first step is short circuit the battery. So if I short circuit this battery, it will be, the circuit will look like this. This is one R, this is another R, this is your C, and this battery has been short circuited, and then there is this resistor. Right beta? Now we know one thing. If battery gets short circuited, then whatever comes parallel to that short circuit, that loses its significance, because no current is going to flow through this part of the circuit when we will apply some external battery sources and all. So whenever a short circuit, whenever, very important point, whenever a short circuit comes in parallel across any circuit element, this circuit element loses its significance, and it is better we throw it out of the circuit. And it is better we throw it what better out of the circuit. So then it reduces to something like this. And here we go. This is your C, this is R, this is R. What is the next step? Find R equivalent by open circuiting the capacitor. So my next step is I will open circuit this capacitor. So I will just show this capacitor by two terminals, and then I have beta R, and then I have this R, correct? This is one R, this is another R, and then I will sit on this capacitor and see what is the R equivalent. Now for me, these two resistors are connected in what beta series. So my R equivalent ka value here is how much beta? 2R. And the value of C was how much? C. So my answer for time constant of this circuit is 2R into C. Clear? I repeat, short circuit the battery, open circuit the capacitor, find R equivalent, sit on the capacitor, find R equivalent. R equivalent will be your multiplied by the value of capacitor, and you will get time constant. What time constant means is it has different significances in different chapters. You will find this term in oscillations, you will find this term in AC, alternating current, you will find this term in inductive circuits, in transient analysis of capacitors and all. In next lecture we will deal with the transient analysis, and there we will understand in complete detail what time constant actually means. Whatever circuits we have done today, whatever theory I have tried to make you understand through these particular circuits, it is very important you go through all these today, and please ask your doubts to us, and we'll try to solve your doubts as quickly as possible. And I hope this session today has cleared many basics which were lying underneath somewhere or hidden underneath somewhere. And now I think even if there are some bigger questions on capacitors, we'll try to take those questions in our upcoming sessions and make you more self-sufficient as far as capacitor circuit problem solving is concerned. Thank you so much, students. Goodbye.